All right, let's try this again. There we go. Again, if you don't succeed, or if at first you don't succeed, reboot your program. Okay, so when we're solving for this guy, one of the things that we have to remember is we've already done it once where we tried to solve for the value. We just don't have enough information without using simultaneous equations. So if we want to solve this guy and be able to get all of the resistance or all the voltage values, what are we going to have to do? Use Thevenin, but where are we going to take Thevenin? Any of the other four resistors. Does not matter. So I2 is 12. Okay, so now what we do want to do is we want to solve for V Thevenin, R Thevenin, the voltage drop across R1, R2, R3, R4, and R5. And we can do this just by Thevenizing in one point. Then we can use that information to go back and recalculate what all those values are going to be. So, for this example, we're going to Thevenize. We don't want to use R3 because that didn't help us out this time. So we can try any one of the other resistors. Let's do R1. So we're going to Thevenize this circuit with R1 removed. Steps are going to be the exact same. So we remove the load. We solve for the voltage drop across A to B. And we solve the resistance for what these 2 points would see. Now this is going to change what resistors are in series, what resistors are in parallel when we look back. So again, more practice at redrawing circuits, because that's one of the things you're going to get. A schematic is not necessarily the way you want to solve it. It doesn't look the way easy to solve a lot of times in the schematic. It's just laid out so you can get everything on the one page. That's also going to be different on how it's visually laid out as well. So there's multiple ways to do this. Yes? Yeah, we'll go through it. Okay. So, first step we've done is remove the load. We want to solve for V Thevenin or R Thevenin first? V Thevenin, okay? So we want to find the voltage drop from point A to point B. How do we go about doing that? Yep, we're going to make a loop. Where do we want to go? So we're going to start at A. Do we want to go left or right? So go, what? Go right. We're going to go this direction. Okay, that's the loop we're going to find. So using this circuit, we have to determine what is the voltage drop in this loop. And it really is that simple. The voltage from A to B is going to be the voltage drop of R2 added to the voltage drop of R3. Okay? Well, where's the voltage going to come from? So let's start with R2. What's the polarity of R2 going to be? Positive on the top, negative on the bottom because of this guy's polarity. Okay? What about R5 and R4? Okay? What is R3 connected to? That's two positives. But What if we were to draw it out and split it out? If we were to take this guy and rotate him down, bring this across, what would be the polarity then? So what this is going to turn out to be is we have our circuit with our battery. We have R2, and what's R2 connected to? R3 and R4. What's R4 connected to? R5 and the negative terminal. And what's R3 connected to? R5 and point B. So if we have a positive to negative, positive to negative, positive to negative, what does that give us for R3? Positive, negative, top to bottom. So now our VAB is going to be the voltage of R2 plus the voltage of R3. Now, can we solve the circuit? So we got 72 volts. R2 is 12 ohms. It was 74. I was just trying to get my resistor values down. Does this circuit look like anything we've done in lab? For those who are a little ahead. Yep. It's just a series parallel circuit that has multiple branches. That's all it is. Okay, so when we look at this, we have 74 volts. We're going to drop 74 volts across R2, and then whatever this equivalent is going to be. So we need to solve for the equivalent of this circuit. So our R total in formula form is going to be equal to R3 in series with R5, these two guys, in parallel with R4 in series with R2. So that's the shorthand of what our formula is going to look like. Now we just have to do these individual steps. So R3 plus R5 is 27 plus 16. That gives us how many ohms? 23? 43. We have 43 in parallel with 15. We should see somewhere in the neighborhood of about 8, 10. How much? And then the last step, plus 12. That's what our resistance total for this guy is going to be. So now we need to find the voltage across R2. So we take the voltage across R2 is we take the 12 ohms, divide it by the 31.121. We multiply that by 74. Because all we have here is we're trying to find this resistance versus that parallel network. I made it up. I wish that time I could blame dyslexia, but that was just not even close. I think what I did is I took that answer and added 11 to it again. How much? Yeah. Well, we're getting it across R3, but it's going to take another step. So now, we've got this voltage across R2. So let's put that on there. So 38.407. Now, from here to here, basically across R4, we have what's left over. So the 74 minus our 38.407. Okay? But we don't care what the voltage is across R4. We're not looking for it. We want to know what this voltage is. But the good thing is, these two are in parallel with this, so that value comes in handy. The value does. We don't care that it's across R4. So now we're going to do our voltage divider again based on R3. So this is where we're going to take this number, because that's the total resistance for that branch. So the voltage of R3 is equal to 27 ohms over 43 ohms, and that's multiplied by this voltage. All we're doing is taking our 74 volts and subdividing it across every other component. So of this portion of the voltage here, we're taking just a portion of it. So we end up with 22.349 volts. We good there? Yep. Because we come back and look, the voltage we're trying to solve for is VAB, which is R2 and R3. We don't care what the voltage is across R5. We know how much is going to be there. It's going to be the rest. So another 13 volts and change. We don't care. We don't care the voltage. All we want is these two. So yes, VR2 plus VR3 is going to give us our VThevenin. So VThevenin, back to our original problem, is VR2 plus VR3, which is 38.407 and 22.349. What did you say, Max? That's what we would measure if we had just this circuit. Because we got to remember, we're doing all this after we've taken a resistor out. So we could rebuild the circuit just like this, measure that voltage from here to here, and we would get the 60.756. That's the only way we could actually accurately measure our VThevenin. But when it's connected fully, the circuit-wise, we're not going to be able to make that change. All right, so that gives us VThevenin. Now, we're going to come back up here to our main circuit. What I want you guys to do, take this home, solve for what our resistance Thevenin is going to be. I want to see you guys practice your redraws. That's what we're looking for. Make sure we can go from this circuit to a redraw. maintain the connections, and if you have questions, like I said, bring them in tomorrow. Any questions before we go? Okay, have a good night.